And I want to talk for a short while about how we find ore deposits and what we might need in the future in terms of metals and what the demands of society might be. So what do the geologists do in order to find more ore? Well, first of all, they use exploration techniques, and one of the key exploration techniques, apart from geophysical techniques, is geochemistry. If you use geochemistry, it gets you kind of closer and closer to an ore deposits. If you do systematic surveys, for example, then you will find where these chemical anomalies are, and this is how you might locate certain deposits. So we can predict from the geological context where we have a high probability of a certain deposit occurring. We can then identify the target sites by doing systematic surveys on the ground, either by surface sampling, by stream sampling, by drill cores, things like that. And once we have identified a high concentration, whatever the type is, we need to assess the stability, the grade, and the workability. So you might find a super deposit, but if it's really remote, like in a polar region or at the ocean floor, you might not find it easy to actually exploit it. The costs for mining it might be horrendous, and then the best deposit is economically not worth a lot, unfortunately. So, and if you don't have the transport infrastructure to take the ore and move it somewhere, it's no good. And can you actually ensure that there is mine safety, that there's ore continuations, that you have enough reserves? Because if you bring a lot of equipment to the North Pole, but the mine is exhausted after 2 years, then I promise you this didn't work financially very well for you. So these are considerations that are quite important. And just very briefly, and this is very simplified, of course, but certain geological environments are more likely to produce certain ore deposits because of the geological processes that are at play. And here we said at mid-ocean ridges, we have these iron and copper and zinc deposits, and we get these sulfide lenses that we could exploit. So we have these volcanogenic massive sulfides here. Then we, a little bit further away, we precipitate manganese. We make these manganese nodules, and they are probably our best bet for more cobalt in the future. And then these would be on the seafloor, strewn on the seafloor. And here in subduction zones, this is an entire subduction zone where we subduct crust underneath thin or forming continental material. And there, depending on where we are, we might go from chromite-enriched areas to very copper, molybdenum, gold, and silver-enriched ones. So this would be like the Andes or Indonesia, where we have these porphyry copper deposits that have low concentrations, but large amounts of rock with this. So we need to shift a lot of material in order to get these minerals, but there is lots of it. So if you're prepared to move entire mountains, as has been done already in the Spanish Empire, this is how the Spanish Empire was financed for a long time, then you can actually harvest these metals from there. And then, we have the granitic intrusions. They are often continental. This is where we have pegmatites. This is what's very important, for example, for hard rock lithium mining, but this is also where we probably get a lot of these Karuna type things. But as I said, there's some debate amongst geologists whether you have this or this setting for Karuna type. I mean, I guess it's somewhere in between in reality, or some are a bit more this way or that way. But it's certainly not an oceanic environment. It's more of a kind of volcanic continental environment. And this is where you would expect these different ore deposits to form. So with this knowledge, you can actually target certain types of things in certain geological environments. Now, this is an interesting kind of concept. I don't know whether you came across this. This was done in the 80s. The Geological Survey of Sweden had this idea that they could save some costs by asking people to send in rocks. If they find peculiar rocks, you could just post it to the Geological Survey next door, and they would identify it. And they secretly hoped that they would find the most important mineral deposits this way, basically using the average population as exploration geologists without them actually knowing, it failed quite badly. So first of all sorts of things were sent in, but most of them had no value whatsoever. And the amount of time they had to spend explaining what these rocks are, it didn't turn out to be a particularly good way. So this is why I'm saying it's not a random process. Not every peculiar looking rock is worth something, unfortunately. So you need to be systematic about it, and you need to have special knowledge, unfortunately. So as I said, this was a lovely experiment, but it was not very successful. So here we need to think a little bit about the resource cycle. So once we have found the material, and once we actually are feeling confident that there's enough of a certain metal and we can get it out sensibly and safely, then we have to kind of think about making a mine of it. And the process from discovering a deposit and making a mine of it, certainly here in Europe, is easily 10 to 20 years. It's a huge, long-winded, painful process, not to mention that local populations might not be happy with it. This is just the legal way of actually getting permission from a government to mine something. So, and I cannot stress this enough, this is not a trivial process. There's loads of things you need to have, your boxes ticked for. And you need to think about the quality of the source. We discussed this at length now, but you also need to kind of show that you have enough money to sustain this, that you can pay your people, that their health and safety is at a certain standard, that you have environmental kind of protection, and that you actually have a plan to make the mine into something friendly afterwards. Often big holes in the ground might become a lake later on and things like that. You need to think about the infrastructure. Can you actually transport these things sensibly and environmentally acceptably? And then, of course, you have to think about the market itself. It's all good and well that there's a high price for this or that metal today, but can you ensure that the price stays high? If somebody finds a similar deposit or a better quality deposit somewhere else, somewhere in Africa where the laws are very different and they can produce huge amounts of this very quickly, your price might deteriorate overnight and all your investment is down the drain. There's this huge problem about De Beers and the diamonds. You might or might not know, but it became possible in the 70s and 80s to make high quality industrial diamonds. And the Soviet Union did this or had several exploration laboratories to do this in a larger scale. And this would, of course, bring down the value of natural diamonds dramatically. When the Soviet Union collapsed, several of these labs fell into private hands. There's actually people in Siberia that are making diamonds. And De Beers is really annoyed about that, to the point that they want to have little engravings on their diamonds to say, this is a natural diamond. So I don't know where the story will end, but these labs are getting better and better at making diamonds that look as if they're natural. One of the problems was they were actually too clean, these industrial diamonds, but now they made the process dirty, so they look like having little inclusions, and they can make them pink now as well, and yellow. So if you are buying a diamond, you need to be a little careful these days. So to get a certified or non-conflict kind of material, metal or diamond, is actually becoming increasingly important. It's a big topic out there. Can we ensure that things are ethically mined, that they come from good sources and they're not kind of cheap fakes, or that they are not coming from areas with well-known child labor problems or things like that. So this is a big effort in the mining industry these days. So, and mineral resources, well, mineral reserves meaning the material we know we can exploit for many metals is often discussed, might actually become exhausted if we only think about the mines we currently have. And in Sweden, mining for traditional metals is going deeper and deeper, but there's loads of iron. But Sweden has no tradition when it comes to rare earth elements. And this is what we increasingly need for electrics and for green technology like solar panels, as well as wind turbines, etc., etc. There's a lot of these in green technology. And there's a huge market for that. But as I said earlier, 95% of these REE, these rare earth elements, they come from China. So in a way, China can, if they want to, they can actually determine the price for this, to the point that Japan has now started to hoard these elements. They have made stores where they hoard 6 months of these supplies for its entire industry, because there's friction between China and Japan since the Second World War. They're not the best of friends. And Japan doesn't want to be dependent on China. Europe, on the other side, is entirely dependent. So we are not in a very strong state if it came to a resource conflict. So, and here a few words about exploration. I mentioned this earlier. And in order to find new deposits, in order to make ourselves independent, we really need to invest. And the EU is investing now for over 10 years in more exploration to reduce the resource dependence, to make us more resilient, but it hasn't yielded any meaningful results, unfortunately. So it's that you have the knowledge and you find these places, and then you need to actually develop them, and then ultimately you can mine. And wherever you have mining and raw material extraction, it's a well-known fact, wealth comes with it. Populations get richer. Living conditions get better, equality improves. So wherever there is large amounts of mining, there is a positive effect for the population. Not strictly around the mine itself. There you might have some damage, like here in central Sweden, in the mining of the last few hundred years. A lot of forest got chopped down. This is not necessarily the best, but for the country as a whole, mining has been hugely beneficial. And as I said, well, if you read that here, it's not a random process. It's a very selective process. And we actually will be demanded to put more effort into these things in the long run. So I don't think we need to go into that in a lot of detail, but the knowledge, the increasing knowledge and understanding of these systems is really, really important in order to create economic value and to market this and to be environmentally good with it, so that your mining doesn't become a disaster, as it's so often the case in less developed countries where environmental policies are not adhered to, where labor conditions are not adhered to, and this is the real problem. So the geology of Sweden, very briefly, for those of you who are interested. So here we have this belt of Paleoproterozoic rocks, and this is a large kind of volcanic area that is very, very old, and this is where most of the ore deposits lie. And it stretches over into Finland and also the Kola Peninsula. So this is the main rocks that have the ores and give the mineral wealth to Sweden and Scandinavia. And here is some information from the Geological Survey. So this is the different mines we have in Sweden. Some of them are no longer active, and some of them were already mined as early as the Middle Ages. So you're going to Sala here. Sala is mined since the late Middle Ages, and the Swedish kings were always very protective of Sala because it was the main source of silver, meaning the main source of their money to finance all these expeditions to continental Europe and fight all these wars and buy more gunpowder from Iceland because you need sulfur for that and all that kind of thing. So Kiruna, in turn, is a very young feature. It was only discovered very late, and most of these Arctic occurrences are very young, and they were the result of geological exploration, and then they found the big ones. These are a bit more random. I think I'm pretty confident Falun and Garpenberg and things like that, they were found as a random kind of occurrence, but today we are kind of using very well-organized techniques in order to find that. So here, up here, we are mining a lot of iron in the Arctic, and there's a bit of gold here and base metals. That means copper, effectively. That's kind of here. And then there's a few mines that are still active down here for copper sulfides and things like that. Garpenberg, Zinkgruvan for zinc, of course. And these are the main active areas. There's no iron mining at this in this part of Sweden anymore. There's a few large deposits like at Grängesberg, but they were shut down in the 80s. Not because there's no ore left, but mainly because of political pressure at the time and because of very low iron prices. So here's a few registered deposits, and here's a distinction between mineral reserves and resources. I mentioned this early, we must make a careful distinction. Resources is the material we understand, and reserves are what is potentially there, where we are confident it's there and we are confident we can get it out, but we're not actually mining it as such. So the biggest reserves are, of course, in the north of Sweden, where we have the big iron mines, and there we have quite a lot of iron. There's loads of iron for the next little while. And in terms of resources, we're also quarrying a lot and mining a lot here in the north of Sweden, far less down here. And largely because of social pressure, there's virtually no mining here. There was efforts to open a vanadium mine in Skåne, and the company gave up earlier this year. And quite some mixed feelings there. Some people think, great that they don't open a mine in populated areas. On the other side, vanadium is now going to be mined somewhere in Africa, usually with child labor and under appalling conditions. So this is the other side of the medal, unfortunately. So by pushing these companies out, we're not strictly making the world a better place. We might make certain areas a better place. So we're outsourcing some of these problems, unfortunately. So this is a big dilemma we are facing, certainly here in Europe these days. So, and a few words about this problem here. So environmental pollution is something that governmental companies like LKAB have really strict regulations. And I have no shares for them, so I don't really have any personal interest in that. But they're at least putting effort into good working conditions, health and safety, environmental remediation, and things like that. While elsewhere, certainly in the Southern Hemisphere, this is not always the case. And there we have situations where leachates are pumped into river systems, where things are burned off. This looks like Falun 300 years ago, where they burned off the sulfites in order to get the iron out. So this is something that wouldn't quite be possible in the Northern Hemisphere these days. So, and of course, here is the other side. I mean, nobody necessarily wants a mine in their backyard. I think that's entirely understandable. On the other side, given the amount of mining that is predicted in terms of satisfying the requirements of modern society and of all these countries that don't have it yet. There's countries in Africa where less than 1% of the population have internet access. Think of how many computers and how many kind of cables we need to put into the system to actually improve that. How much copper will we need for that? It's mind-blowing. It's staggering amounts. So, and it's not Europe, it's not North America that does that. It's in Asia where most of the action happens. So this is global production of metals without iron. So this is copper and zinc and things like that. And this is from the 1980s to a few years ago. And see how Asia is kind of, increasing. Europe is actually going down. North America is going down. Latin America is fairly stable. Asia, and to a large part, China, is really taking up most of the challenge there. And for us, we're buying the things there, but we have very little control of the exact conditions under which they are doing this mining. So here, the EU import reliance. It's all good and well to get companies to stop mining. But for cobalt, we are 32% reliant on imports, for zinc 61, for chromium 74, for tin 78, and if you go further down the list here, platinum, titanium, tantalum, rare earth, niobium, even rubber, molybdenum, antimony, we are 100% reliant. So if there was a global crisis, we could be cut off this very easily. So it's actually quite a disturbing thought, to be honest. Much of Europe, and in fact North America as well, has outsourced these issues. It's almost a modern form of colonialism, if you ask me. And we are buying these things under enormous costs in terms of transport and carbon budget to get these things here. But it's still cheaper. So here's a few more kind of plots to give you a sense for this. So this is iron, and this is what the EU produces in terms of iron. This is what we could potentially recycle, and this is what we're importing. This is copper. This is what we produce. This is what we could recycle. This is what we are importing. So when people argue, we could recycle, no, we can't. There's just not enough here. We're miles away from that, unfortunately. So here's the same thing for aluminium. And think of lithium. For batteries, we want to have electric cars here. Whoa, the amount of lithium we need is just mind-blowing. Not to mention things like tin or platinum, kind of, yeah. So here's the world production for certain things, and actually it says hafnium in France. This is not quite right. This is that France buys it from its former colonies, refines it, and then puts it out on the market. So this is artificial. Europe actually produces virtually nothing. So most of it comes from Asia, and in fact from China, and partly from Russia, and partly from South America. And this is where Europe, as an economic entity, is almost entirely reliant on external resources. So this is known ore deposits in Europe, and this is what we actually do in terms of exploration. This is where exploration activity goes. The different colors are different types of methods and different types of ore deposits. We don't have to go into the detail this afternoon, but here you see that there's loads of ore deposits. We're not looking at them. Not here, not with me, but we're actually not very good at recycling at this point. So there's a lot of technology that we need to develop when it comes to, for example, gold recycling is a classic example. The amount of gold that is known to be, for example, in old mobile phones, old computers, just in Germany, for example, is on the order of 6,000 kilograms per year. This is huge amounts compared for gold, but we don't have the means of getting it out at this point. So recycling is not very efficient. I think estimates have it that we need another 20 years before we can really recycle our needs to a degree that it becomes satisfactory. Until then, a lot more mining needs to happen, and likely, given that every system is notoriously inefficient, Newton's third axiom, everything kind of has problems and fails somehow, it's going to be more than 20 years if you ask me. So, but there's detailed numbers out there. I can look them up for you, and there's actually some papers in Studium. There's the Vidal et al. Article in Nature 2013, and they go into that a little bit more. So you can find detailed numbers there, and they're quite explicit. We are miles away. It's a wonderful idea, but practically we're not there by any close margin. So, and then when we look here, Swedish exploration permits from 2000 to 2020, they're actually going down. This is when the EU announced we need to get more resilient. There was a short kind of lift for a short while, but now we are back on track for going down. And this is, of course, a bit of the dilemma I'm describing. And I don't have the answers. It's not for me. I don't really kind of have a personal interest there. But there is this mismatch between our needs and what most people actually think we want. So, and this is a bit difficult. And I'll try to put numbers on this now. So this is what we need for copper requirements for electric vehicles. A conventional car needs, and this is in pounds, this is a US source, and here, a conventional car needs between 18 and 49 pounds of copper. If we think about a hybrid electrical vehicle, and we don't even like them anymore, we want proper electrical vehicles, it needs 85 pounds. If you go for a battery electric vehicle, it needs 180, factor 10. And if you think of electric kind of large vehicles like trucks or buses or things like that, whoa, get the factor? It's enormous. So it's very staggering where to get all that copper from. So, and this is not just that. So here's an electric car, and this is not just copper. There's all the other elements we need. This is a conventional car. This is an electric car. So you need huge amounts of these other elements as well. Nickel, lithium, manganese. And this is just mind-blowing. There's people in the sector talk about a disconnect between what a lot of people argue we should do and the amount of materials we need. So here's some numbers, what we would need in order to electrify the traffic. And wow, I'm just blown away by the numbers. So if you look at the numbers, there's real issue. And not to just leave it with electrical traffic kind of attempts, but if you think of offshore wind and onshore wind, solar and nuclear and things like that, even nuclear, some people argue it's the answer, it's environmentally more friendly if it's safe, but even that needs huge amounts of more metals compared to some of the traditional ways. And that's not an answer either, we know that. So we have some real issues, some real dilemmas to fix. And this is a paper that only came out last year, and I think I have a reference here somewhere. I don't know whether it's coming up. Here it is, Vattari et al. 2020. I just put it on Studium 2 days ago for you. This is kind of projections for our needs, and they are distinguishing between low-carb technology and other uses. And I don't know, you need to read the details about how they define these different things. But for all of these metals, you can see the pink area is the projections for the future up to 2050. Whoa, this is where we are right now. So I don't know where to get that all from. This is why people like Elon Musk want to go to space, because there's loads of it out there. But getting that here will also cost us a lot of mining, of course. So I don't have the answers, as I said, I repeat myself. But the problem is by not mining it under controlled conditions, we are accepting these problems, like polluted rivers, like large spoils in the landscape, like oxidizes and dead ecosystems. And this is what we have, for example, in areas like Congo, where most of our cobalt is coming from. A recent study has even shown that the children in the mining district in Congo have DNA changes by now from all the poison in there. This is not funny, it was a Nature paper. And they can really link this absolutely clearly to the dirty mining practices. So I'm personally very torn, because while mining has a bad reputation in Northern Europe, at least it's done in a reasonably clean way, while this is not always the case elsewhere. So, and not to mention that in many parts of the world, small people are favored for mining because you have to go underground, and this might not be age dependent. So there's huge problems with, for example, child labor in Congo. And if you have a mobile phone, and if you have a battery-driven car, if you have a Tesla, I promise you, there's cobalt from Congo in there. So here, the cobalt problem. The amount of cobalt we will need in order to electrify our traffic is quite enormous. Passenger electric vehicles for batteries, portable batteries, like in your mobile phone, they all require cobalt at this kind of point in time. And this is projections up to 2030. Even if we want to, we're not getting enough cobalt. We have a huge deficit, and that is not even stopping the mining practices in Congo. So this is why people are saying we need to go submarine and harvest these manganese nodules. But then we're facing a new problem. We're actually going to destroy these ecosystems at the ocean floor. There's species we haven't even discovered. They might be dead by the time we're getting this cobalt up. This is a wicked problem. Honestly, wicked in the sense that there is no clean answer to this. So, and of course, here's the other kind of side of the medal. If we look at the sustainability goals, then, well, we need to do this in order to kind of satisfy all of these things. This is central to it. Without actually kind of, creating wealth, we cannot fix this problem, and this problem, and this problem, and this problem, and this problem. In areas where mining happens, we create wealth, we reduce poverty, we increase equality. Whether you like it or not, this is one of the downsides. So this is a very complicated system, and it requires huge intellectual capacity and effort in the next decades to fix. So there, people talk about what's known as the sustainable development paradox. And I'm not kidding you. So the thing is that a lot of people say, oh, you can ride a bike or eat less meat. Quite frankly, given that Europe is only producing 7% of the global carbon budget, whatever you do is almost insignificant. So we have some global problems that are so big that a huge effort is required. And personally, I'm a little concerned about that, if you ask me. So is space mining the answer? I don't know. Maybe it is. We'll talk about space mining in the next few days. And at least there is no ecosystems we are messing up. We might not have environmental problems with CO2 in the same way. But before we can actually go to space and mine it, it's going to take us another 20, 30, 40, 50 years before we are technically there. So this problem is not going to leave us alone for a little while.